Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 65. Expert Cross-Examination Table. Preemptive Answers. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We have reached the final step of Book 12, the book of Expert Scrutiny and Legitimacy. We have built the Holophase framework from the ground up, defended its mathematics, mapped it to measurement and falsifiability, connected it to information and topology, and separated it clearly from worldviews or belief systems. Now we stand in the final room, under the sharpest lights. This is the room of cross-examination. Here, four expert voices sit across the table from us: a physicist, a mathematician, a linguist, and an information theorist. Each brings a lifetime of training in their own discipline. Each has hard questions. Each wants to know whether the holophase is just a beautiful story or a serious proposal that can sit beside the best ideas of modern science. Today, we walk into that room and answer them, calmly and clearly. Think of this part as a rehearsal for the toughest seminar you could imagine. The aim is not to win an argument with clever words. The aim is to show that the holophase, when probed from different angles, keeps giving coherent, testable, structurally precise answers. By the end, you will not only hear those answers, you will also learn how to think with them, so that you yourself can stand in that room and speak on behalf of the framework with clarity and confidence. Let us start with the physicist, because physics is where the strongest contact with experiment lives. The physicist listens to the opening mantra about phi and may immediately ask a blunt question. How does this relate to the field theories we already have, like quantum electrodynamics or general relativity? Are you simply wrapping existing theories in poetic language, or is there a real structural gain? The honest answer begins with humility. The holophase is not here to replace successful physical theories that already predict experiments to astonishing precision. Quantum electrodynamics, for example, already describes how light and charged particles interact, using quantum fields, creation and annihilation operators, and path integrals. General relativity already describes how spacetime curves around mass and energy, using a metric tensor and curvature. These theories are not broken toys. They are cathedrals built over a century of work. What the holophase does is different. It does not try to demolish those cathedrals. It tries to reveal the shared architectural blueprint that runs through them. It says, if you look beneath the details, what both theories are doing is this. They pick a field or set of fields, which you can call phi. They use derivatives of those fields through space and time to express curvature, slopes, and rates of change. Then they write constraint chains, differential equations, that link those derivatives. Those equations are the grammar. The outcomes we measure in the lab, like energy levels, particle trajectories, or gravitational lensing, are the meanings of the sentences produced by that grammar. Seen this way, quantum electrodynamics and general relativity are not rivals to the holophase. They are examples of it in action. So when the physicist asks where the new content is, we answer. The new content lives in the global organization, in the insistence on tri-unity, and in the demand that every serious model be tested in time, space, and motion simultaneously. It is like giving physics a new coordinate system on the space of its own theories. In that new coordinate system, Connections between domains that once seemed separate become easier to see. A vortex in a superfluid, a defect in a crystal, a flux quantum in a superconductor, and a skyrmion in a magnet all become different expressions of the same topological letters written in different media. This does not change their equations overnight, but it guides us to look for shared patterns and shared experimental tests. The physicist's second question is more practical. What concrete predictions or advantages arise from this framework that could motivate a busy lab to care? Here the answer is about discipline and methodology. The Holophase triunity rule says, if your model only predicts a time series but ignores spatial structure, it is incomplete. If it only predicts spatial patterns but ignores motion, it is incomplete. This is more than philosophy. It is a design principle for experiments. It encourages building setups that measure, for example, both the spectrum of a wave and its full spatial profile and its propagation speed, and then demanding a single derivative-based model that fits all three at once. Models that pass this triple test are much more trustworthy. Models that fail it reveal exactly where new physics might hide. Next, the mathematician takes their turn. Their concern is not emotional persuasion, but formal clarity. When they hear about a master tree of derivatives, they want to know whether this is truly a well-defined mathematics or just an image. Here, the answer is crisp. The master tree is the intuitive picture of something that is already well known in differential geometry, the infinite jet bundle. At each point of spacetime, instead of only looking at the value of a field, we consider the value of all its derivatives at that point. First order, second order, third order, and so on. This infinite list is called the jet. The space of all such jets, over all points, forms the jet bundle. Physical laws written as differential equations can be seen as conditions on which jets are allowed. In other words, they carve out a subspace of the jet bundle. A real physical history is a path through spacetime whose jets lie inside that subspace. The master tree is simply this structure, seen through the eyes of the working mind, rather than through the symbols of pure mathematics. The mathematician may then ask about convergence, because infinite towers of derivatives can be dangerous. Real fields can be rough, noisy, or even singular. Here, the Holophase answer is technical but clear. The infinite tower is the conceptual ideal. In practice, we always work with finite truncations. We keep derivatives up to some order and drop the rest. This is exactly what is already done when we use Taylor series or effective field theories. The Holophase proposal is not that nature literally hands us infinite smoothness everywhere, but that physical modeling can be understood as the art of choosing how high up the tree we need to go for a given phenomenon and precision. The framework encourages systematic study of how predictions improve as you climb the tree and of where they stop improving, which often signals a genuine singularity or a need for a better underlying phi field. Then the linguist speaks. They hear the word language and immediately want to know if this is more than a metaphor. Human languages have alphabets, syntax, semantics, and pragmatics. Does the Holophase really have analogs of these? Or are we stretching words beyond usefulness? The reply begins by respecting the depth of linguistic theory. We admit that Holophase is not a human language. It does not have arbitrary signs like the word tree. But at the structural level, it does have all the elements of a formal generative language. The primitive operators, like taking a derivative in time or space, form a finite alphabet of operations. Composing them builds more complex words, like curvature, divergence, or acceleration. Constraint chains act as grammatical rules. They specify which combinations of words are allowed. The tridimensional echoes are the semantics. The same rule, applied to the same initial data, always produces the same observable behavior. Finally, the scientist and the world together provide something like pragmatics. Experiments are questions, outcomes are replies, and the evolving research program is the conversation. The linguist might still worry. Where is the discreteness that characterizes language? Here, the topological alphabet enters. Even though the values of fields and derivatives are continuous, certain structures built from them are necessarily discrete. winding numbers, defect charges, flux quanta. These are like robust letters that survive noise and deformation. They behave much more like the symbolic units linguists are used to. In information technology, such robust discreteness is the foundation of digital coding. In Holophase, it emerges from the continuity of phi itself. So the framework truly has both smooth analog aspects and deep discrete ones, unified by topology. At this point, the information theorist leans forward. They have heard about bits, entropy, channel capacity, and computational limits for decades. They want to know whether Holophase is compatible with that entire edifice or whether it contradicts it. The reply is that Holophase does not compete with information theory. It supplies the physical body in which information theory lives. When we talk about bits, we are always talking about stable, distinguishable patterns in some field. A voltage high or low, a magnet pointing up or down, a molecule present or absent. Each of these is a particular arrangement of phi and its derivatives. When we erase a bit, we force phi from a more specific pattern to a less specific one, dissipating energy. When we send bits down a channel, we create time-dependent and space-dependent changes in phi that fight against noise and loss. The widely successful formulas of Shannon and Landauer give us the limits on such processes in terms of probabilities and energies. Holophase gives us a language to describe the detailed shape of the underlying patterns in a unified way. With these individual cross-examinations answered, we can now see the deeper pattern. Each expert is, in their own language, asking the same two questions. First, is the holophase structurally precise enough to connect to my field without hand-waving? Second, does it expose new tests, new comparisons, or new syntheses that are worth my time? The answer in each case rests on the triunity of time, space, and motion, and on the commitment to falsifiability. For the physicist, triunity means building experiments that test all three echoes at once. For the mathematician, it means embracing the full structure of jet bundles instead of thinking only in terms of fields and their values. For the linguist, it means recognizing that semantics in physics is always tridimensional. For the information theorist, it means treating bandwidth, storage, and computation as tri-echo manipulations of phi patterns. Another way to see this is to imagine a mixed panel, where all four experts sit together and listen not only to the answers, but to each other. The physicist may notice that the mathematician's jet bundle language gives them new tools to think about effective theories. The linguist may notice that the information theorists concerned with codes and noise provides a natural way to talk about robustness of topological letters. The mathematician may notice that the linguist's emphasis on syntax and semantics clarifies the role of constraint chains and solutions. In other words, the holophase serves as a kind of translation layer between disciplines, allowing ideas from one domain to be mapped into another more easily. This is not a vague hope. It is already visible in smaller ways in contemporary science. Techniques from information theory are used to study neural coding in the brain. Topology developed by pure mathematicians now shapes our understanding of condensed matter systems. Wavelet analysis developed in signal processing helps analyze turbulence. The holophase framework says these crossovers are not accidents. They are symptoms of an underlying structural unity that can be made explicit. That explicitness, once fully developed, will make such interdisciplinary borrowing more systematic and powerful. You, as a listener, might wonder what your role is in all this. You may not be a professional physicist, mathematician, linguist, or information theorist. Does this cross-examination still matter to you? The answer is yes, because it shows you how to think critically and generously about ambitious ideas. It teaches you to ask, whenever you hear a grand claim, a simple set of questions. What is the structure? How does it touch data? How could it be wrong? How does it speak to different expert communities? By watching the holophase go through this process, you learn a general pattern you can apply elsewhere. It is also important to notice what does not happen in this cross-examination. At no point does the holophase ask any expert to abandon their existing successful theories. It does not say to the physicist, forget quantum field theory, It does not say to the mathematician, forget your rigorous definitions. It does not say to the linguist, forget the complexity of human language. It does not say to the information theorist, forget Shannon. Instead, it says, keep all of that, and let us look together for a deeper pattern that runs through them. If the pattern is real, it will make itself useful by clarifying, organizing, and sometimes extending what you already know. If the pattern is not real, if it breaks under close examination, then it will quietly fade and the disciplines will go on. In this way, the expert cross-examination table is not a trial in which the Holophase must defend its honor. It is a working meeting in which the framework is taken seriously, challenged sharply, and either improved or rejected on the basis of shared standards. The questions we have written here are only a first draft. As more experts read, listen, and respond, better, sharper, and more detailed questions will emerge. New parts of the framework will be tested and refined. Some branches of the master tree may be pruned or regrafted. This is healthy. It means the idea is alive. Let us now step back and return to phi with this final layer of understanding. Phi is proposed as the unified field whose derivatives give rise to all the echoes we see. That proposal is not protected by poetry or by personal authority. It is exposed to physics, to mathematics, to linguistics, to information theory, and to any other discipline that cares to join the conversation. Each field brings tools, questions, and standards. The Holophase answers as best it can. Where it answers well, it gains credibility. Where it fails, it must change or give way. This is what it means to be a scientific framework rather than a worldview. As we finish Book 12, you can feel the shape of what we have built. We began by introducing the Holophase language, one field, its derivatives, and their three echoes. We explored how this language organizes physical laws, information, measurement, and topology. We clarified what it is not mysticism, not a belief system, not a vague metaphor. We showed how it can be tested, reproduced, and potentially falsified. And now, we have rehearsed how it can stand up to expert cross-examination. What remains in the wider journey of the Holophase program is to keep walking this path in real time, as actual experiments, papers, critiques, and refinements unfold. For you, as the listener, this closing movement is an invitation. You are invited to carry not just the content of the Holophase, but the way it has been tested and questioned. You can bring that pattern of inquiry into any area of your life where big ideas appear. Ask for structure. Ask for contact with reality. Ask for clarity across disciplines. Ask how something could be wrong, not just how it could be inspiring. In doing so, you become part of the same spirit that built science in the first place. The conversation about reality is far from over. The Holophase offers one way of speaking in that conversation, one candidate grammar for the universe. Whether it will endure is not up to belief, but to time, evidence, and the collective work of many minds. What matters now is that it has been put on the table with enough clarity and courage that it can truly be examined. Before we leave the physicist, it is worth addressing one more likely challenge. What about quantum weirdness? A sharp-minded physicist might say, classical fields and derivatives are fine, but the heart of modern physics is quantum theory, with superposition, entanglement, and operators that do not commute. Where do those live in this picture? The answer is that Holophase is agnostic about whether phi is classical or quantum. In a quantum setting, phi is promoted to an operator-valued field. Its derivatives are operator derivatives. The master tree now lives in a Hilbert space setting, but the structural idea remains the same. Dynamics is still expressed through constraint chains that link derivatives. Superposition and entanglement then describe not a different kind of reality, but a different style of pattern in the same underlying grammar. The fact that quantum predictions are probabilistic does not break the language picture. It simply means that the sentences of the world are sometimes best described statistically, using amplitudes and density matrices as higher-level words. The mathematician may raise an equally shallow point. They might say, jet bundles are one thing, But modern mathematics also uses category theory, measure theory, and functional analysis to study systems. Does Holophase ignore these, or can it speak to them? Here, the reply is that Holophase is not tied to one particular branch of mathematics. Jet bundles are a natural way to express the local derivative structure, but the framework can be recast in many other languages. For example, one can view the evolution of phi as a functor that assigns to each time slice a space of field configurations, and to each time interval a morphism between such spaces. One can study measures over the space of field histories and interpret statistical mechanics or quantum path integrals as measures on spaces of holophase sentences. In this way, holophase is not a competitor to advanced mathematical languages. It is a theme that can be orchestrated in many styles. The linguist might also want to press further on ambiguity and recursion. Human language is powerful not just because it has words and rules, but because it can embed clauses within clauses, generate infinite sentences, and leave room for multiple interpretations. Where is that in holophase? The answer is that recursion is built into the derivative tower itself. A derivative of a derivative is like a nested clause. It says not only that something is happening, but that the way it is happening is itself changing in a structured way. As for ambiguity, in physics we see it when multiple models feed the same data within error bars. The world has spoken a sentence, but we have more than one possible grammar that could have produced it. The holophase does not remove this ambiguity. Instead, it helps us organize it. Different candidate phi fields and constraint chains become alternative parse trees for the same observed story. Further experiments act like additional context that resolves the ambiguity. Meanwhile, the information theorist is likely to ask about algorithmic complexity. Shannon's framework tells us about average information in a distribution of messages, but Kolmogorov complexity asks about the length of the shortest program that can produce a specific pattern. Can holophase say anything about that? It can, at least qualitatively. A simple physical pattern, like a pure sine wave, corresponds to a very low complexity holophase description: a single dominant frequency, a simple wave equation, and a few parameters. A turbulent flow, by contrast, corresponds to a highly complex description: many interacting modes, cascades of energy, and a need for high-order derivatives or very long constraint chains to describe it fully. In this sense, the algorithmic complexity of a pattern is mirrored by the structural complexity of its holophase braid. The more intricate the braid of derivatives needed to produce it, the longer the effective program. It is useful to ground all of this in a concrete imaginary experiment that would make sense to all four experts at once. Picture a simple physical system, a vibrating drumhead. The physicist sees a two-dimensional membrane obeying a wave equation, with modes and overtones. The mathematician sees a partial differential equation on a domain with boundary conditions, with eigenfunctions and spectra. The linguist sees a system that can produce a rich variety of patterns in time and space, each pattern like a sentence composed from a basic alphabet of modes. The information theorist sees a channel. Hit the drum with different taps, and you can encode and transmit patterns of sound. Now, through the holophase lens, all of these views become coordinated. The drumhead's displacement is a phi field over a surface. Its time and space derivatives form a local jet. The wave equation is the constraint chain. The overtones and normal modes are structured letters. The sounds heard at a distance are the tridimensional echoes. Changes in tapping patterns are changes in the sentences sent through the channel. All four experts are simply examining different projections of the same underlying holophase story. In your own life, you can think of simpler examples. A traffic flow on a busy road is a phi pattern. Cars as moving packets, their density and speed forming a field. A traffic engineer uses equations that look like fluid equations, talking about density waves and jams. A mathematician can study those equations as nonlinear conservation laws. A linguist can see rush hour as a daily narrative with an opening, a build-up, a climax, and a release. An information theorist might see the flow of vehicles as a capacity-limited channel for moving people and goods. Underneath these metaphors, the same core structure appears: a quantity varying in time and space, constrained by differential rules generating waves, shocks, and patterns. That is holophase in action on the street outside your window. The more you practice this way of seeing, the less mysterious the cross-examination becomes. Experts are not gatekeepers guarding a secret castle. They are specialists in different aspects of the same tapestry. The holophase, if it is successful, will not erase their differences, but will give them a shared underlying map. The physicist's equations, the mathematician's structures, the linguist's theories of meaning, and the information theorist's bounds will all remain important. The gift is that they will be able to talk to each other more easily and to collaborate on problems that once seemed too fragmented to approach as a whole. Finally, we should acknowledge the emotional side of this journey. Big unifying frameworks can trigger hope, excitement, skepticism, or even fear. Some people long for a single deep story that ties everything together. Others worry that such stories slide too easily into ideology. By emphasizing the expert cross-examination table, and by keeping the focus on reproducibility and falsifiability, the holophase deliberately chooses the harder path. It does not ask for comfort or reassurance. It asks to be questioned, challenged, and, if necessary, corrected. That is why you have heard so much in this book about tests, gates, mappings, and protocols. The strongest beauty an idea can have is the beauty it retains after its hardest critics have taken their best shots. This, then, is the spirit.